it's Sean from Having Fun Repairs, and welcome back to my channel. We are going to start a new restoration series, and I'll get into what we're restoring here in this box in a second. Now, to go ahead and get out of the way the typical opening spiel, if you enjoy my channel and you're new to here, please consider subscribing. If you enjoy this video itself, let me know by giving a thumbs up or even a thumbs down if regardless of that option really provides any data for you as the viewer. I see that data when I am using YouTube Studio application. And also consider leaving comments as we go along on this restoration. As a matter of fact, the previous restoration I did for the 1949 Zenith All-American 5 radio, the comments were absolutely helpful for me in learning more about what I was restoring. And then lastly, if you're not aware, I do have a Patreon now, and in which I am early releasing videos every month. So I typically try to film a month in advance so I can schedule out my public release videos over YouTube throughout the month. I have a lot going on between my actual job and school and being a husband and a father. So the best way for me to be able to provide content is to record in advance by at least a month's worth of content for you all as a viewer. But on my Patreon channel, I'm not only releasing, say, this month what is January, so all my content for January is already released over on Patreon versus it being scheduled out here, but I'm also providing exclusive content teaching TMDE or test equipment basics, as well as we'll be teaching electronics principles and electrical engineering fundamentals over on my Patreon. Again, those videos, that type of content will be exclusive to Patreon and will not be up for public release. So if you enjoy learning more, and hopefully I present it in a way that is easy to understand and also fun to follow along in, please consider joining me, becoming a subscriber, a member of my Patreon. Now, moving on, let's get to what's inside this box. You might have seen me pull this out before, but if you haven't, this is a analog volt-ohm meter or multimeter that I acquired sometime in the past. That's definitely in need of a bit of restoration. Just looking over the case itself, I mean, when you consider trying to restore something, you want to try to keep it as original as possible. But other than the aluminum on the case, you know, some mild rust and on the case itself, the paint's pretty much gone, so we'll be stripping off all the old paint and redoing it. But concerning this analog multimeter or volt-ohm meter, I will do my best to keep the faceplate of this multimeter as original as possible and just clean it up. Now, if that means while I'm cleaning that some of the paint comes off or it's patinaed a bit, then so be it. Maybe we'll just clear coat it. I'm not too sure how I'll approach that just yet, but over time I'll give several considerations along the way. So we're going to try to keep this as original as possible, minus the cosmetic things that we do need to address, simply because you want this to look somewhat presentable. You know, many different things and other restoration type people have their own approaches and their own opinions. But, you know, I've got mine, and I'm already kind of got my mind made up on how I want to move forward to a certain extent. Maybe throughout the video I'll change my mind and waffle a bit, but I'll try not to. But anyways, let's discuss this volt-ohm meter in and of itself. Now, this is a multimeter that was produced here in the United States. The manufacturer was Triplett Electrical Instrument Company out of Bluffton, Ohio. I believe this specific multimeter was made in 1939, at least from what I can gather from radiomuseum.org. Now, the company that made this was originally founded in 1904 in Bluffton, Ohio by Ray L. Triplett, and initially called Triplett Meter Company. It was housed on the second floor of a building on Main Street in Bluffton. The first product that the company developed was the hot wire meter, which was housed in a nickel watch case. The first meters were marketed under the name Pocket Meter Company. However, in 1932, the company name was changed to Triplett Electrical Instrument Company. That's a bit of a background. Now, this multimeter, if you haven't noticed, there is no plug coming from it. So believe it or not, comparable to our modern handheld digital multimeters, this was a portable device, which made use of a 4.5 volt dry cell batteries. And something I think worthy to note is this multimeter itself was also used by U.S. forces during World War II. So I think we have a lovely bit of history here. Now, I tried to find some pictures online of a World War II era technician, either avionics or Signal Corp or radio man, making use of this multimeter specifically, but I couldn't find a photo as such. Maybe some of you will be able to discover one, but I can imagine using this as a field technician of sorts, based upon my own service in the U.S. military, and then what I do day in and day out with my job. So this would have practical application in the field. At the time, it would be highly portable, and I could see somebody needing to use this to make measurements on any electronic device or radio RF generating system, or even an aircraft of that era, and I can picture that in my head, and maybe you can as well. Now, I kind of want to go over the diagram real quick and just give you my initial thoughts on what I see according to the diagram and some of my concerns. Okay, and here goes our diagram. Well, not a whole lot going on here, really. We can see several resistive or resistor networks, which would be fairly easy to troubleshoot with a digital multimeter to see if they're in tolerance. But and we can replace them with something a little more modern. It appears we have one capacitor down here, approximately 50 microfarad at 600 volts, most likely. If I had to guess, maybe a paper foil capacitor, especially given the use of a dry cell battery for our supply. And it also looks like we may have essentially two diodes facing each other. If I had to guess, possibly acting as a form of ESD clamp for protecting our circuitry, and most likely additional protection for our 100 microamp or 100 millivolt meter over here, in which we would get the display for our voltage measurements, both AC and DC, as well as our resistive measurements. Now, my primary concerns, resistors, not too concerned about that. Capacitor, not really too concerned about that. But this network here with our diodes, I'm slightly concerned with. So I'll be definitely paying attention to here, as well as this dry cell battery. Now, unlike wet cell batteries, a dry cell is, as name implies, there is no liquid per se to spill out, but I could imagine, depending upon the age of this battery, there could still be quite a bit of corrosion. So it's just some things to consider once we open up the device and start digging into it. Which brings us back now to this voltmeter. It came with some test leads. Now, whether they're still usable, I think is rather debatable. They don't appear to initially be in the best condition, but we could take a bit closer examination of them a little bit later on. And if need be, we could probably either refurbish them or find a suitable replacement. As far as getting into this voltmeter, it appears to be rather simple, as I only see 4 screws holding the faceplate to this multimeter into the chassis in which it resides. Now, no operations manual came with it, but here's also the schematic that I did find in there, in which we can potentially use without having to go unnecessarily to the schematics I got off of radiomuseum.org. So this is rather nice to find. So why don't we get this taken apart? This was fairly easy to take apart, as you just watched, but man, what a mess did it make. As you can see on my desk, my bench top here, the amount of debris and dirt in there. I kind of wish I was wearing gloves at this point and a mask. To be honest, the debris, as it started to disperse from a settled state up in the air, created for me a bit of a coughing fit. Inside our case, yeah, I've set it aside for now, but along with our probes and the diagram, you could see the amount of rust in the debris and material that's accumulated over time. So that's something that we will definitely have to address. But almost it's kind of those things that kind of make you not want to do a restoration. I knew this one was going to be a bit of a project to tackle. But just having a device from this era is totally worth it. So we'll see how this goes along. What can we say about the components that we have inside? Well, other than looks like a nut and a screw that sheared off somewhere in there. We'll have to figure out where that goes. But as suspected, we got a nice size wax covered paper and foil capacitor here, most likely bad. We will take this out and measure it, and I'll actually throw it up on the oscilloscope and we'll see how it compares to a modern equivalent. The manufacturing of this appears to be typical for the era. We're talking about point-to-point soldering, an old school wiring loom that we have here, and then of course the our conductors themselves are wires, making use of a fabric outer insulator instead of your traditional plastics or or rubber type materials used today. Good news is there was no battery inside, and the leads for what would be tied to the battery are not in too bad of condition. We might replace them regardless, but they appear to look pretty good. Hopefully I don't eat those words. But we definitely have quite a bit of soldering that we're going to address. Our resistor networks, as I mentioned, we'll make the measurements, but most likely we're going to be replacing these. I will go out on a limb and assume that these are probably 1 watt resistors here. But if you look down in this way, it might be a tad bit harder for y'all to tell, so I'll try to cant this up a bit. We have somewhat more old school wire wound resistor. 4,000 is what it's rated for. Which would absolutely dissipate quite a bit of heat, depending on how much current is going through it. So I'm going to have to determine what the actual power rating is for it, and then my assumption would be somewhere in the neighborhood of 2 to 4 watts, but I could be wrong. For those of you who are more familiar, you let me know, and hopefully our diagram actually has an indication for it. Otherwise, we're going to be doing some calculations ourselves, and we'll see how that goes. Our actual selector switch seems to be in fairly good condition, albeit dirty. We will have to address cleaning up these different plates we see in here, but we're going to have to be careful with how we clean it, because you know, I can use isopropyl alcohol or QD electronic cleaner, but we want to make sure that we are not leaving any residue, because if you do, then that's going to add resistance between where the switch makes these pins coming off the switch make contact with the plate underneath. And then if you affect that, then obviously you're going to have an effect on whatever you're measuring, which will have an effect on whatever you're reading out on your display. So just some things that you have to carefully consider. The chassis of this as well is coated in some form of, well, this right here seems to be just a high gloss paint, maybe some form of conformal coating, but you also feel the same type of conformal coating, or you know, in some regards maybe it's like old candle wax or something on the other components as well, which I would assume, given the nature of the device being portable and the application for it in field conditions, that was probably a way of keeping your internal components protected from certain elements, so that way you weren't shorting out anything when you were having to use this out in the field. Concerning that diode I discussed earlier, the two ones facing each other, I believe that's what we have right here. It's kind of sitting in this can, although we do see a resistor sitting on top. I'd have to go back to the diagram, but they're not. It's not my modern diode network you see in here. I think I do not know. I believe this construction of these diodes are not like our modern silicon diodes, but most likely selenium. So that being said, anybody watching this who actually knows, you let me know, but that is my guess at this point. Looks like we have one carbon resistor in here as well. Yeah. Hopefully our wires remain good. I will do my best to clean these up and keep them intact as much as possible without having to replace them. And hopefully we don't have to replace every resistor we find in their own networks as well. Hopefully a few of them measure within their range. That way we could try to keep this as original as possible. But I would honestly like to be able to use this and to trust the readings I'm getting, because essentially, you know, an analog multimeter is still a good asset to have as far as your own lab in your home. They are just a lot more sensitive, in my opinion, to the measurements you make, especially once you have a range of deflection within the needle here, and how quickly you see it move based upon, you know, the increase or decrease of the amplitude of whatever AC measurement you're having. You see that reaction within the meter a lot quicker than what you do with a digital multimeter, and however that circuitry is set up and gates per se. So our 0 cal is here, and looks like that potentiometer is still intact, and I'm not seeing anything significant with the wires, albeit a bit of corrosion down in this area right here. But again, there we go, right down there. You could probably see that brighter colored wire down in there. But again, you know, just some small things that we'll address over here. But of course, all the small things eventually add up to one big thing. We'll see how this goes. So is this going to be a one-shot video restoration? Most not likely not. Is this going to be a 4-video restoration? Again, most likely not. What I'd like to do is address cleaning this up and getting several of these components replaced in here. I'll probably record some of it, but not all of it. We are going to build our own DC supply to be able to use inside this multimeter, since we no longer have a dry cell battery. And we're also going to have to address the case. Now, I don't know if I'll be able to fit it all into 2 videos, but I can't foresee anything more than 3. So I know my restoration videos go a bit long, but I do that primarily. There are those of you who enjoy watching a video and have the time to sit down for that duration, but I also understand not all of you can, so I'm sure to include chapters tabbed out so you can move around while watching this restoration and seeing the key points and stuff like that. But the primary reason why I take my time and try to record as much as possible is because I'd like for these restorations to be able to be an avenue for of a historical record per se. So that way we have an opportunity to see history and the repair of history in fine detail, I guess. Now, barring how these diodes function, we probably could replace them with a modern silicon equivalent. So that's something that I'm going to have to consider as well. But for right now, I think it's time to try and clean this up a tad bit, and then we'll start measuring a few things. So I've got it a tad bit cleaned up, and what I did was I just dampened the cloth and went around to wipe off our faceplate here. I didn't want to use any other type of detergent or cleaning method because I'm really concerned about the paint. I didn't scrub too hard on our meter here because I'm somewhat worried about breaking this glass, even though we have a bit of buildup still around it. Will be taking out this meter, but we need to be especially careful with it because of just how sensitive the needle and the armature and the components are of this meter as is. Which, speaking of which, I found out where that one broken off nut and sheared off screw went, and it was actually down in here, see if I can get this on camera for you, but down in here where you see the tip of my tuning wand going, which corresponds to this screw right here. So that's where that went, and maybe we can find a replacement screw. If not, then so be it. But with it cleaned up a bit and a little more additional time looking over our schematic here, and the what's provided from what was it, the radiomuseum.org, everything is in French, so I had to do a bit of some translation. But this diodes that we see here, I assume they're offering ESD suppression. This French word that you see here, redressure, or however you pronounce it, actually translates to rectifier, which actually now makes sense given when we follow our path here. We're essentially in our selector switch down at the bottom of our diagram, it's used in conjunction with a resistive measurement, so we don't have direct battery voltage for that measurement. As the negative lead is tied to one side, our rectifier is supplying a voltage through these resistors, this resistor network, in order to provide us a measurement in resistance. So it's basically setting up a voltage divider. I think that's the best way I can explain it, and measuring the difference in order to give us a resistive value or resistance measurement. But anyways, I wanted to take a closer look at our resistors here. Now these are all, if I'm not mistaken, wire wound resistors, just like what I mentioned with this bigger old school dog bone resistor here and here. Now dog bone resistors, if I'm not mistaken, are going to have a pretty wide tolerance of like 20% or something like that. Whereas I assume the tolerances will be a lot tighter on these other resistors, especially the ones you see here that look like they were essentially manufactured to a specific value, because we have some very weird values on our diagram here that are awfully specific. So I assume that these were manufactured, I don't know, somebody sitting in a plant with an insulated conductor, wrapping them around a pole and then cutting them until right when they measured within whatever tolerance of the value that was needed, and then soldering the wire on either side of these posts. Speaking of which, we have one that's disconnected here, so right off the bat we've got ourselves a concern, and then hopefully this underside's not broken. So if we have to replace one, it most likely will be this one right here, at least from a visual inspection. But if you don't know the power dissipation that's needed, or the power factor of your resistor, there are a couple things that we can do to make that determination. So for instance, we'll just use this resistor right here. Now this is a 4K ohm resistor, R23 or R20 according to our diagram here. Here goes basically whatever this French word is, stands for plaque A, which has our C41, our big capacitor sitting here, and then the resistor right next to it is R20, which is a 4K ohm resistor, and like I said, that's a dog bone resistor, so we're going to have approximately, I assume, a 20% tolerance. But we need to know, what is the max voltage if I have leads sitting in here that will make use of that resistor under measurements, that way we know what the power rating should be for that resistor. Where there's a way that we can go about it. What I'll do first off is I'll put my negative probe. Now I've got this in a resistance measurement, as you can see there, but I've got my negative probe into the common on the front, and you know, essentially the ground or common, and we can cycle through our switch and the top pin to this resistor to see where we get connectivity, and you can obviously see it there. Now, because this is a series of resistors, the total value leading up to this is, you know, just under half a megohm, or just over half a megohm, or 500 500 and slightly greater 1,000 ohms, until we get to the let's see, 500 volt AC measurement. And again, we're going common to the positive lead, and you can see that this resistor is essentially tied to our common, which obviously is right here. So yeah, that's going to be the bottom half of our resistor, and we're taking that measurement right off the top here. So obviously we can see that 4K ohms of resistance. Now, we can't just do that, and we also need to take it from the positive side. So this will be AC. So I'm going to put my black probe into the AC hole, as you can see right here. And then we're going to take the same measurement off the top of that pin. And what are we getting? Here we go. 585 megohms. Now, if we go to the bottom lead of that resistor, you can see that, oh, I don't think that was the right one. Let me find it here. I think that's it. You can see 581 megohms, essentially 580, 581. So that would make sense that you know, depending on what side of this resistor we're on, how are we measuring it in series with the actual circuit. Oh, wrong one. Here we go. And on one side we do, and on the other side we do not. So you might be mistaken at first that, okay, so we're going to see 400 volts AC max applied to this resistor, and that's actually not the case, because our positive lead is the one that we're primarily concerned with, but there will not be current flowing through it if the negative lead it cannot be seen with our multimeter here on the other side once the switch is selected. So depending on where the switch is at. So at minimum, right now, concerning AC measurements, we can have the potential of 500 volts AC going through this resistor with a total resistance in circuit of 585,000 ohms. Let me write that down real quick. So we've determined that this resistor is definitely in circuit with a AC measurement of 400 volts AC, and we know in circuit our total resistance is 585 k ohms. So what would be our what would be the power rating of our resistor? Well, essentially we are going to square our voltage, so 400 times 400, and divide it by our resistance. Let's first do that, and then we'll take that number and divide it by 585,000. So in this regard, that resistor could be potentially slightly more than a 1/4 watt, so maybe a 1/2 watt. But you know, that's not the highest voltage on our scale. Let's consider our DC voltage, and we have a 1500 volt position. Let's take a look at that. So again, I'm going to go from negative to, well, we can go to the top, and we're not getting any connectivity, but I'm not sure if I really trust that, given we do have some resistors that are broken on our board. But from the positive side, we are definitely there at a total resistance of 585 kiloohms. So we could do, actually, let's get to the bottom of that one. 585, 581. Yeah, there you go. You see the difference. At 585 at 1500 volts. And if we were to do a calculation on it, let's see, 1500 times 1500. All right, divided by our total resistance, 585,000, and we're essentially looking at a 4 watt resistor. So, you know, just something to consider. But what about our tolerance, right? So I'm going to carefully set this face down, and we are going to take a measurement just across the resistor, and we are getting 4.017 KOhms. So let's write that down, 4.017 K. Now, is this within tolerance? Well, there's math we can do for that as well. That's 4,000 times 20%, so 0.2 would be 800, right? So you could be between 4,800, or let's see, 4,000 minus 800, because I suck at math in my head. Yeah, it should have been easy. 3.2 thousand ohms. In which case, if we are looking at our value here, 4.017 K, I would say that resistor is within tolerance. So at this point in time, what I'm going to do, and I'm not going to record all this on camera because I really just can't see this video spanning too many for a restoration on this multimeter. I'm going to use my digital multimeter to check all my resistors and write the values down, and then go through and see if they're within tolerance, and then come back and let you know what I find. Well, many hours have passed by this point, to be honest. But what can I say with all the gibberish I have on my paper here, and little annotations and stuff? Essentially, I've checked every resistor in here minus those inside of our rectifier. I'm going to check this in a different fashion here in a second. Might be a tad bit of a risk to do what I'm about to do, though. Anyways, concerning the resistors that we have, everything on this this placard here, all those values, including these dog bone resistors, were within 1% of their assigned value. So that was really nice to find out. However, well, before I get to that, for the most part, these wire wound resistors that you see here built in this fashion, they as well were roughly 1, and then a few were at 5% of their values. But for the most part, they were in 1% of their assigned value. And then obviously this one that is broken away, we'll solder back down. We'll actually do that here in a second. Now, on to these specific. Now, I wouldn't know really what to call them, whether they're ceramic or a wire wound resistor sitting inside of a glass tube. This one over here is actually the ceramic or glass is busted. But all of these type of resistors now, they come with the Triplett name on them, and then their values stamped on as well, although most of them have faded at this point. But you see their values are often pretty specific. Well, maybe not these within our circuit here. 1 meg, 350 K, 100K, 35K, 10K. Those will be fairly easy to find a replacement for. But when you get into these very specific values like 9.331K or 933.1K, those values aren't essentially something that you just readily create yourself with your traditional packaged resistors like you see here. It's not something you can do. Now, if you were to build your own resistor using, enameled wire as such, you could probably get away with some of the lower values if you have enough of this enameled wire to build your own around these old basically posts where they're wrapped around. You could probably do something like that, but I wouldn't recommend it. But my primary concern is all of these style resistors we see down in here. We see over on this side, this one here, and then of course these ones that are obviously viewable here, they're way out of tolerance. I mean, greater than 20% of their assigned value. Now, is that important for a device that for the metrology of this device? I would probably think so, especially given the fact that we're using this to make accurate measurements. So we'll see what I can come back with, and honestly this might end up being something that I won't be able to restore, which would be unfortunate. But I've at least got the values and recorded down, and we can check those out. But that's essentially it. And I think I'm gonna solder this guy right here down real quick. Absolutely for us, and not gonna take very long to do. Okay, just gonna be careful not to get solder anywhere else other than this post and other side of that wire there. Probably could grab some tweezers or something in my drawer here. A plethora of tweezers in there, but I always like going to my go-to pair. That should do it. Now, the other thing I probably should have mentioned is we also have this 2.5 k-ohm potentiometer sitting here on our diagram, and I measured it out to be 4.5 k-ohms. So you would think, yeah, that's pretty high. But I'm not too concerned about that, because essentially this potentiometer is this guy right here, and it's specifically designed to allow for us to zero out our multimeter. But I know I haven't replaced this capacitor yet, but taking off my wedding band, but we're going to attempt to power this up for a second. I'm going to start at a lower voltage than started at around 3 volts. I'll do 3.5. Then can I go up to 4.5 from there? Sure can. All right. We'll start it at like 3 volts, and then I'll increase it from there, and just keep my eye on my DC power supply. See how much current we're drawing. Hopefully we don't have any issues. Hopefully no fires get started. Probably should move this paper out from underneath it. Okay. And well, any deflection here? At 3 volts. Let's increase it up a tad bit. Let's go to 4. Yeah, I have no movement in the armature, and I'm not drawing any amps, so that's not looking good for our rectifier there. Okay, let's turn it off. I'll attempt to get it off 4.5 volts. See if we get anything then. And if there's no life, then we can assume that this right here is bad as well. Yeah. Absolutely nothing. We'll put it down to 1,000 ohms. And just take this 10 ohm resistor. Well, I don't think the leads are going to fit. Can we go from the back side? Yeah, I don't get anything. Well, let's see. What if we do a 1 megohm resistor? Yeah, absolutely nothing. All right. So most likely that rectifier is bad as well, and obviously I'm not drawing any current from my DC supply, so but I guess that is what it is. Something we're gonna have to figure out. Well, with realizing we cannot take resistance measurements, will at least allow us to take voltage measurements. I've hooked up these super janky leads. And we're going to cut our voltage down to something like 3 volts. And I'm only doing a DC measurement. Alright. Ground probe on. And I've got this up to the 5 volt range scale for DC, and we'll see if we get any needle deflection. And we do get a tad bit of deflection in our needle, and now it's gone because I messed with this pot. Obviously it's not where it ought to be. On the 5 volt scale, DC scale, that would put us on this scale right here, and we are measuring less than a volt. And as I increase it, see, right about 4.2 volts out, I've got a volt on the meter. Eight volts out, I'm starting to see 2 volts on the meter. So we at least have some life, but definitely not accurate. Man, I really hope that our meter isn't bad, although I highly doubt it is. I would assume most of our issues are right here within the device. So, well, that gives us some more data to go off of. And now to bypass the leads in their entirety, I'm going directly to the back side of these jacks, and we'll see what happens. That's a volt, and I am seeing not even a volt on our scale. Right about 4 volts, I see 1 volt on our scale. 8 volts, I get 2 volts on our scale. So obviously we got some things that are way off and wrong. Okay, now the next thing I've done is I've went ahead and removed this 0.5 microfarad 600 volt paper foil cap, completely wax coated. I want to test it out. First we're going to check to see if there's any stored voltage on it, and it doesn't really appear to be the case, so we should be able to take a measurement on here. We're getting 690 nanofarads. Wow. So if it was at value, we should actually be seeing about 500 nanofarads, because that would be 0.5 microfarads. I wonder if I got any other caps of the same value laying around. And unfortunately, I do not. The closest thing I have is a 0.05 microfarad 600 volt orange drop cap. But these won't work. This is like a modern equivalent of what you would have here, but it's just not at the right capacitance rating. So that's something that we're going to order as well. But I kind of do want to look at one more thing on this, so give me a second here. I've got my oscilloscope set out and SIGGEN. Set our frequency to 100 hertz and 10 volts peak to peak. Okay. And for our oscilloscope, let's see, channel 1. Looks like we're on ground here. And channel 2. That looks like we're on ground as well. Switch over to XY mode, and yep, appears we are on our center radical. So let's turn on our SIG. Turn back off channel 2. There we go. And got our probes hooked up. SIG hooked up to our curve tracer here, and let's take a look at this cap. See what its characteristics are. And ooh, it's like it's not even there. Not looking like a capacitor. One would assume. Well, it is quite possible that that cap filters out anything below 100 Hertz. So why don't we start bumping our frequency up 10 Hertz intervals, and we'll see what corresponding change we get on the oscope. And it appears like any frequency below 320 is completely filtered out. Now we're starting to get a phase difference. Right about 660, what was that, 620, 630, we have a full elliptical. And I'll keep bumping it up. Getting to about 3 kHz. Going past 3K. Alright. Well, now we're starting to look more like a capacitor. And so that at least tells me that we can use this to compare it with whatever replacement we get, so we can have a better analysis of how well that capacitor is functioning. I think that's pretty cool. Well, ladies and gents, I think that's going to do it for the first episode of our restoration on this multimeter, or VOM meter that we have here. We plainly have quite a few components that we need to get on order, and quite a bit of work to accomplish in restoring this. So if you've enjoyed what has been shown thus far, please consider subscribing to my channel if you haven't, and liking this video if you already have. And also, if you're interested in what a curve tracer or octopus can do for you and increase your ability to test components within your own bench or setup, by all means, I share content over on my Patreon. The last video I did was specifically on this device. And but anyways, I appreciate your time. Thank you for watching. Take care and goodbye.
Mark?